Okay, off we go. So last time, and I didn't have my thing up. Sorry, I forgot to put the thing up here. Let's see here. This is Chapter 7. Okay. Right. So we were right along in here, as I recall. We were talking about gravitational fields, and we wrote down a couple of things, sort of preliminary observations. So the gravitational field from a point mass, which, by the way, not really physical. That's actually good news, not bad news. I'll explain that in just a second. But when you have hypothetically a point mass, and here's the formula for the gravitational field created by that point mass. Now here's, again, it's sort of a bad news, good news thing. What's bad about this vector field is that it has a singularity at the origin. And remember, a lot of the stuff that I've said about how Gauss's divergence theorem works and the various other theorems that we've talked about, right, is that they are very delicate, and if you're going to use the theorems, it requires that the vector field be as, quite nice, right? No singularities among other regularity constraints. And so this having a singularity, we have a problem. All right, so the problem, though, is directly related to the fact that it is a non-physical hypothetical point mass. And in the actual physical world, of course, there is no such thing as a point mass. Right? Mass is always distributed over some volume, however small. So anyway, so the issue with the singularity here that looks like it's going to just torpedo everything that we want to do, turns out it's not a problem. Okay. So I'm going to sweep that under the rug. And we made this observation that this vector field, being as it is inverse square radial, it's just like a point light source. So, I mean, it's as if, and therefore you can pretend that mass does not just magically create a gravitational field that's just kind of there. Right? You can think of it as that mass is kind of like little light bulbs, except instead of shooting out photons, like a point light source does, it shoots out little particles called gravitons. Right? And if this were true, hypothetically, if this were true, well, then we would get exactly this formula. For the, how many gravitational, what is the flow field of the gravitons that are being emitted by mass? Well, it would look exactly like this. So, again, if something behaves as if a certain metaphor is true, then you can just pretend that certain metaphor is true, and you won't get any wrong answers. So that's what we're going to do. And by the way, I strongly encourage, when you're thinking about gravity, again, weird though it may seem, I'm always thinking of gravity from the point of view of gravitons. It doesn't matter if it's true, right? But it behaves as if it's true, and so it's a perfectly reasonable game to play in your head, if nothing else. Okay, so I think where we ended last time is I made this case that this equation right here is plausible. Idea being that if you have mass on the inside of some surface, doesn't even really matter so much about the surface. The surface has to be a boundary of an enclosed interior, right? But doesn't have to be any surface in particular. Well, however much mass is on the inside, keep in mind what mass does. Mass shoots out little gravitons. Right? More mass, more gravitons. And of these gravitons that get shot out of the mass, how many of them flow out of your surface? All of them. Right? So the amount of flow of gravitons through your surface, namely the flux of the gravitational field, it's just proportional to how much mass there is. Mass creates gravitons, gravitons creates flux. Right? So highly plausible, right? This is very physically and geometrically just like, well, yeah, I guess that's sort of how it has to be. And this very convenient foot in the door allows us to write down some really powerful conclusions. So in particular, let's look now at this equation. Other than this constant minus 4 pi g, which is just that's just the what the proportion is between mass and how many gravitons it shoots out. Other than that, this equation just says mass is a triple integral of density. That's old news. Nothing exciting on that top row. Okay, easy result. What we have down here is just the divergence theorem. Right? And so the result then is that we have that these two integrals are always equal for every solid region. And again, I appeal to your intuition. If two integrals are always equal for every region, no matter what region you pick, they're always the same. Oh my God. It must be that the two integrands are equal. And so what we have here is a remarkably, otherwise remarkably difficult conclusion to try to conclude, that if you have any distribution of mass, right, over some region, that distribution of mass is going to create some complex gravitational field. Every little particle of mass in which creates its own little gravitational field. So all these gravitational fields, they all kind of superimpose, and it's a bonkers complex situation to try to write down the actual gravitational field. But the divergence of that gravitational field, mass density, it's as simple as that. I mean, constant times mass density. So really, really powerful conclusion, without having to go through the preposterous complexity of what this gravitational field would be. And it all comes about from two things: thinking of gravity as communicated by gravitons, like a light bulb creates photons, and Gauss's divergence theorem. So really powerful ideas, super powerful ideas. Okay, and I also, by the way, like how this rolls off the tongue really nicely. This equation right here. Flux comes from mass. Simplifies very nicely in these sort of differentially per unit volume form of flux density comes from mass density. Right? Flux and mass, flux density and mass density. That's pretty cool. Okay. All righty. Now, next, we're going to talk about electric fields. And you may be thinking to yourself, and I thought this too at some point, that, look, gravitational fields, unless you're going to become an astrophysicist, most of us deal with a pretty simple version of gravitational fields. It points down, that's it, right? It's pretty simple, right? So understanding complexities of gravitational fields, what's the point? Isn't this an exercise in nonsense that has nothing to do with us? Most of y'all are engineers. Now, I hope and assume that you're already persuaded that you will have to understand electric fields. Electric fields are not, in our everyday experience, very simple, right? There's all sorts of weird electric fields going on inside of all sorts of electronics. So why did I start with gravitational fields? And the answer is gravity is much more relatable. It's much more everyday experience. Again, you just can't live on this planet without understanding gravity, right? It permeates everything we do. And with that in mind, the math of gravitational fields and the math of electric fields are practically identical. The only difference is the the physical sort of realities that they talk about. But the math is the same. So, in particular, in the same way that mass creates a gravitational field and thus a gravitational flux, likewise, charge creates an electric field and thus an electric flux. And by the way, just so you know, the inverse square radial gravitational field, well, structurally, identical to the electric field, also inverse square radial. The only difference between the gravitational field and the electric field is, there's constants. Some of those constants are involved in the fact that sometimes the electric force is attractive, sometimes the electric force is repulsive, right? But whatever, that's the plus or a minus, and that's ultimately just some different constant. But it's inverse square radial. It's structurally identical. And so I propose, and I think this saved me so much like agony and pain when I was trying to learn about electric fields and E&M, Physics 152, I guess it is, right? And then after that, by the way, and I don't know if engineers have to take this, but there's an advanced E&M course, right, that I had to take, and that's pretty hardcore. Anyway, how do you think about electric fields? Think gravity. And when you're thinking gravity, you're thinking little particles shooting out of the mass, right? So likewise, you can think about electric fields as representing the flow of little particles being shot out of charge. Not mass, but charge. Everything else, all the math is the same. So you get these wonderful conclusions, immediate and convenient and physically relatable because of the connection to gravity, that electric flux is just proportional to enclosed charge. Nice and simple. And divergence of the electric field is proportional to charge density, namely charge per unit volume. It is totally analogous to these arguments up here about how we related these two statements. The same picture in your mind. Okay. All right. So I'm just a big fan. By the way, for your reference, these two equations here are known as one of Maxwell's equations, two different forms of the same Maxwell's equation. There are four Maxwell's equations, but they both come in an integral form and a differential form. And so, the connection between those forms, how do you relate this equation to this equation? Ultimately, the thing that lets you connect them is Gauss's divergence theorem. Right? So this is one of the big, powerful reasons why it's really important to understand Gauss's divergence theorem. And if you can't, if your schedule will allow it, to make sure that you understand Gauss's divergence theorem before you go trying to learn E&M, because E&M ultimately is this great big physical manifestation of, in this case anyway, it's just Gauss's divergence theorem in the physical world. Right? Divergence is the density of the stuff, namely the stuff that creates the flux. That's what it is. So the divergence theorem helps you understand E&M, and E&M is a physical metaphor to help you understand the divergence theorem. So very closely connected ideas, and I hope that you all will find that useful. Either for making sense out of the E&M that you already had to take, or having a huge advantage when you take E&M in the hopefully near future. Okay, so moving along, we're going to go on to the next boundary theorem, accumulation theorem, whatever you want to call it, density theorem. The next theorem that follows the same model of every other theorem we've been focusing on here. So just again, to remind you of the structure, we need to get precise about what we mean by boundary. I need to identify what is the relevant accumulating quantity. Once you know it's an accumulating quantity, you make the case that, well, therefore it behaves like stuff, like every other kind of accumulating quantity we've talked about. And if it has stuff, then it has location, and you can talk about the associated density. And then you can put the pieces together to form a theorem. Right? Structurally, it's exactly the same as Gauss's divergence theorem, Green's theorem, the 2D divergence theorem, fundamental theorem of line integrals, fundamental theorem of calculus. All of those theorems follow this same pattern. So anyway, let's dive in and see how these details happen to work out. And moving more quickly than we have on the previous theorems, because again, we've really hit all these ideas, except for a few details. So starting with, What do we mean by a boundary? Reminder, orientation, right? So before this course, the idea of a boundary was that, well, it's the border between what I'm talking about and not what I'm talking about, right? It's the fence between my set and not my set. It was just a set itself. That's all. So now we're figuring orientation into the thing, and here we go. So let's suppose that I have some surface, and very importantly, not just a surface, but an oriented surface. Keep in mind that an oriented surface has the orientation given by a normal vector, right? A unit normal vector. That's it telling you which direction is what we're calling the positive direction through the surface, right? So that's this story here, right? So you have your surface, and well, I could think of the surface as, that's the positive direction through it. Or I could think of the surface, same surface, thought of as that being the positive direction through it. So that distinction is called the orientation. So here's the rule for how to orient the boundary. Right? So the boundary of a surface, of course, is going to be a curve. Let me get rid of the mess so we can see this better. Let me redo this then. So here's the curve that is the boundary of that surface. And of course, there's two different directions that I could go along the surface. Which way should the orientation be? And the big idea is that when you're talking about an oriented surface, the boundary is oriented. It's oriented according to a certain convention. The convention is arbitrary. Effectively, somebody just made this up 150 years ago or something, right? Totally arbitrary, but it's highly standard at this point, and again, it's not optional, and so this is, we all have to get on board with it, so it is required, etc. And here's the rule. The rule is always go along that boundary curve in the direction that you get by the following process. The process says take your surface normal that came with your original surface. Put your thumb in the direction that surface normal is pointing. Right hand, by the way, very important. Right hand. It's got to be your right hand. Your fingers, of course, want to sort of bend around the axis defined by your thumb in a certain direction. That defines what I'm going to call a swirl. All right, so imagine that there's kind of a swirling happening, therefore, on this surface. And now you just want to ask, as the normal vector in question, whatever point you're looking at it on, as you kind of get closer and closer to the edge, that swirl, you'll notice, is going to, what I like to call sideswipe. It's going to sideswipe up against the boundary in a particular direction. And the direction of the sideswiping, that's the direction of the proper, what we call induced orientation on that boundary curve. So that's how it works. You're going to notice, by the way, that the direction is kind of compatible, at least as I have it drawn here, appears to be kind of compatible with this idea of, as you're walking, the region is on your left. Doesn't that kind of smack of the Green's theorem sort of precursor, convention on orientation? It kind of feels like it's the same. The difference, of course, here is that this being in 3 dimensions, right? When you have an oriented surface, right, that orientation could be downward. And that kind of changes everything, right? So your thumb that makes your fingers do like this, that seems consistent with Green's theorem. Well, if the orientation is downward, then now look at my fingers. My fingers go the other way, right? So it's not as simple as clockwise, counterclockwise. It really, importantly, not that simple. You have to play the hand game, or I suppose, I mean, if you really wanted to avoid the hand gesture issue, one thing you could do, I do not recommend this, but you could, oh gosh, I was going to try to draw a, boy, this is hard, oh man, okay, let's, okay, there we go. So there's a surface that's kind of wrapped under itself, right? And one thing you could do is, given an orientation, right, you could, and again, I don't particularly recommend this, you could imagine that here's me, right, and I'm walking along, and I'm going to walk in the direction that has the region on my left, right? Again, very sort of familiar and satisfying. As long as you make the little person here, as long as he's always got his head pointing in the direction of the orientation, yes, then it will always be on that stick figure person's left. The problem is you're going to find yourself on an exam thinking about, all right, so my surface, let's see, it's oriented downward, so I have to imagine, and you're going to be contorting your head around. It's just unnatural, right, and weird. And why would you do that? It's so much easier just to take your thumb and just turn your thumb down and play that game. It's just geometrically much easier to work with. Everybody buy it? Okay. All right. So, that's how boundaries work on oriented surfaces. So off we go. We have an accumulating quantity. I claim that the accumulating quantity is boundary circulation. Oh, wrong stylus thingy. Boundary circulation is our accumulating quantity, just like Green's theorem. I mean, it's going around boundaries of surfaces in space instead of going around boundaries of just two-dimensional regions in the plane, but still boundary circulation. So a lot of people very reasonably like to think of this theorem that we're in the process of developing. It's called Stokes' theorem. What we're heading toward is just kind of a three-dimensional version of Green's theorem. That's a very reasonable point of view in a lot of ways. Right? So yeah, boundary circulation. And it accumulates for reasons, I'm going to say, just practically the same reason as with Green's theorem. And the big idea is, yeah, when you cut it in half, yes, there's a kind of a new edge, and the boundary circulation along the boundary of that is that way, and the boundary circulation along the boundary of this is, again, with the orientation rules, that way. And notice that this new edge appears twice with opposite orientations. They cancel. How many times have we seen that before, right? Very familiar. It's practically the same picture that we drew when we were talking about Green's theorem and the internal cancellation of boundary circulation in that context. Morally the same reason here. How we doing? Is everybody with me? You buying this? All right. Okay. Now again, I've made the following argument before. The big case to be made, and this works for any accumulating quantity, really, that you can think of it as happening on what I'm going to call the interior, in this case, the surface whose boundary curve we're interested in. And in fact, it says so right in the name, right? This is our accumulating quantity is boundary circulation. So yeah, it's computed on the boundary. Yeah. But please don't think of it as happening on the boundary. Right? What we want to think of it as is that this is something we associate to a surface. You give me a surface, I will take its boundary and compute the circulation. But in particular, I take the boundary, which means I start with something that is a surface whose boundary blah, 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 right? But the surface is the thing. And so this is a quantity that we associate to the surface. And if you want to know how much of our quantity in question for that surface, how much of that is coming from a particular little subset of the surface, yeah, okay, we'll compute it. And the whole is the sum of the parts. And if you want to know how much is in there, compute it on there. It's just like any other quantity, any other accumulating quantity for a region. Right? So again, we think of it as on the boundary. It's in fact much more reasonable and much more convenient for sure to think of this as having location in the interior, and therefore it behaves like stuff. Very surprising, very weird to think of it that way, but think of boundary circulation as being a stuff distributed over the interior. All right, which means, like every other stuff, it has an associated density. Stuff per unit size. Right? Now, the stuff in question is circulation. So we call this circulation density. Again, echoes of Green's theorem, right? Same sort of interpretation that we made then. It is a density in the sense that we're talking per unit size, where size is area. All right, so again, it's not per unit volume, it's per unit area. And this is our thing. This is our tool that we're going to be using, circulation density. And it has a formula. Again, I'm not going to do the details of the computation. They're in the book if you want to see them. And it is important, but it's not going to come up really in this course. The punchline is what is important, and the interpretation, of course. And this is the formula. It's curl dot orientation. That's the formula. So you're going to see in the theorem that we're about to write down on the very next scroll here, when you see this thing, when you see curl dot orientation, that's your density. That's the stuff per unit size. Is that cool? All right, so let's put the pieces together. Here we are. Let me make it bigger for visibility purposes. So yeah, pieces fit together just like they always have. We have this quantity that we've decided to give a name to. We call it circulation. It's not just a formula, it's a quantity. We're giving it a name and a notation. We use sigma, just like we did in chapter 6 for circulation. It is an accumulating quantity. And again, as before, the whole is the sum of the parts, right? And so, immediate consequence of the fact that it's an accumulation is that the whole can be thought of as just adding up over the surface, all the little individual parts. Okay? And the density we make use of by observing that stuff, as with all stuff is stuff per unit size times size. And there's that density, right? The stuff per unit size here, curl dot in, and stuff is stuff per unit size times size. It's all good? Yep.
Is that normal normalized, right?
I'm sorry, say again, please?
Is the normal vector normalized?
Yeah. Yeah, that's right. So when we talk about an orientation, right, orientation always means a unit normal vector.
Okay.
Right, absolutely. Yep. All right. Everybody good? Okay. All right. Now, having done that development, and I like doing the development this way so that we see all the familiar, oh my gosh, it looks just like Green's theorem, and I encourage you to go back to chapter 6 and look at the analogous, again, deliberately laid out on the page for maximum visibility of the analogy. Notice, oh my gosh, it's morally the same argument, different details for the different context, right? But having done that, it is actually pretty convenient to then notice that, look at that, the in from our density and the ds from the fact that this is, we're rewriting this as a scalar surface integral. Well, yeah, but in ds, pair up to make our ds vector. And so this makes for a nice little rewrite. And even though the development, I think, looks nicer like so, when we write down the theorem day in and day out, I like to always use the easiest notation that we possibly can, the easiest and most natural notation, and this is a slightly easier notation. I can get slightly more natural notation to represent a flux, which ultimately, unexpectedly even, right? We were thinking about how stuff adds up. The stuff is a scalar quantity. Circulation is a scalar quantity. We're adding up scalars. We were expecting a scalar surface integral. Coincidentally, unexpectedly, it happens to work out to be a vector surface integral. How we doing? Everybody with me? So again, the analogies, bonkers, off the chart. Please make sure to do that A-B comparison between Green's theorem and this theorem. Great intuition to be had by sort of importing all your Green's theorem intuition into this new context, and that'll help you tremendously in understanding Stokes' curl theorem. Okay. All right, let's do one. Y'all can probably kind of see this coming. Let's see here. So we're going to compute a line integral. So it says they give us a vector field. They give us a curve. Y'all may recall, by the way, the very first example that I did when we did Green's theorem. It's very much like this. Compute a line integral with a vector field given, with a curve given. And like that example too, if I remember correctly, notice I'm giving the curve pre-parameterized, right? And now that's a distraction. By the way, again, not because I'm just trying to be mean. I'm trying to point out what y'all will be facing in your futures. And in your futures, sometimes the right way to look at a problem might not be the one that is the first one that occurs to you. It might not be the one suggested even by the way the question's written. Right? Sometimes you'll see a curve given to you parameterized, strongly, seemingly suggesting that you should compute the line integral from the parameterization, which we know how to do. We could totally do that, right? Plug it in, do the pullback, right? Turn it into a single variable calculus problem, get away from all that scary multivariable calculus, right? Very, very tempting. Notice, though, how bad, could be worse, of course, but, X would be trig, Y would be trig. That means this vector field is going to have a lot of trig with stuff done to it. Is going to, I'm not saying we can't do it. I'm saying it's not pretty. Right. Okay. All right, so we're going to take a different point of view on this. I'm going to start with my first worry. My first worry is if I want to use this theorem to compute a line integral, Stokes' theorem is about a line integral. If I want to make this work, notice that my curve has to be a boundary. Again, not for sort of like, minor, subtle formality reasons. Our entire argument that built this theorem came from the idea of boundaries. Right? So you take that away and there is no theorem. And more to the blunt point, not only is there no theorem, there is no surface whose boundary is that curve, and therefore there is no surface over which to even talk about a related surface integral. So again, it's not, in the case where your curve is not a boundary, it's not that these two integrals aren't equal. It's that there is no surface integral to even compare it with, to even hope might be equal. Does that make sense to everybody? It's a really big condition. Make double extra sure that if you're going to use Stokes' curl theorem, you better make sure that curve's a boundary, or else you're writing down absolute meaningless nonsense. Yes.
Can you clarify again how you know the example is a boundary?
Well, yeah, I haven't gotten to that yet. Yeah. No, I'm just doing the sort of the build up. Yeah, right. So, no, great natural. Next question: how do we know this curve that we've been given? How do we know if it is or isn't a boundary? And well, this is just a geometry thing, and you just have to kind of draw the picture and look at it, and just use your geometric intuition to find, hopefully, a surface for which it is the boundary. So here we go. Our curve. This curve is given like this, and you can use your previously established skills for parametric curves, right? And what do they look like? And you notice this is a circle in the xy plane. You notice that minus sign. You kind of have to think through the orientation. But the punchline is this curve is that right there, oriented like so. Yeah. Notice 0 to 2 pi, which means it goes all the way around. Right? Now I ask, is this a boundary? Now, a lot of you who have been, appropriately concerned about orientations that I've been pushing so hard, right? We'll look at this and say, aha, oh, no, look, it's oriented the wrong way. Isn't it supposed to go counterclockwise? I hear where you're coming from. But remember, now that we're dealing with surfaces, right? Surfaces can be oriented surfaces can be oriented in one of two ways, right? And just a heads up, in this case, notice that this surface, this disk in the xy plane, if I were to orient it downward, right? I'm going to choose to do this, free country and all of that. If I were to just decide, I would like to consider that surface to be downward. There's the normal vector, right? Then you play the game, thumb down in the direction of the orientation. Right hand. Got to be your right hand. So important. Thumb down, right hand. Look at my fingers. Right? And that makes a swirl, which gives me an orientation, which, sure enough, is the same direction as the orientation of my curve that I was given in the first place. So that purple curve, yes, indeedy, it is a boundary. It's a boundary of the oriented. Here, let me erase just for clarity. This surface that I'm calling S, oriented downward, that I get to choose because it's my surface, right? Nothing in the question said anything about a surface. I'm creating this surface. I can set it up however I like. That surface, oriented downward, orientation and all, is going to give me the correct boundary and correct orientation. How we doing? All right, so we're in business. Our surface is, wrong color. Our surface is, our curve is a boundary of a surface. I therefore have a new surface to talk about whose boundary was the original curve. And we're in business, and we can totally use Stokes' curl theorem right here, and here it is. Again, my curve is a boundary, and Stokes' curl theorem gives me this flux to be computed over my new surface. Everybody see how all those pieces fit together? Right. Okay, so it's all over but the shouting at this point. Again, I want to remind y'all, I've made this observation before, that these are theorems, not magic tricks. Just because you apply Stokes' curl theorem, that doesn't mean you have automatically solved the problem. It means I've turned one kind of an integral into a different kind of an integral. So it's something to try. It's kind of like integration by parts in that sense. Integration by parts turns one integral into another integral. which may or may not be better. Very often is, right? Appropriately selected, but you have to hope that it actually is helping you out. And as it turns out in this case, our vector field being that, you can compute the curl. Make sure you can do the mechanics, right? The logistics of computing the curl of that vector field up there. Various partial derivatives, right? Organized as a little 3x3 symbolic determinant. We wrote that down back in chapter 3. Make sure you're good to go with that formula. You're going to be able to turn the crank on that for, quickly and reliably. And there's dangerous little minus sign oopses that you can accidentally make. Make sure you don't accidentally get a sign error when you take that determinant. It's very delicate. Anyway, there's the curl. As previously discussed, we already knew our normal vector, right? We set up our orientation so that the boundaries would work right and all that stuff. So there's our normal vector. Lucky in this case, very conveniently, just straight down 0, 0, -1. Right? And so our integral has turned from unhappy, difficult, right? This is a I don't want to have to do that line integral. And what I see is by using Stokes' curl theorem, my new option is to compute that integral right there, which I claim is really, really nice and simple because, look, we got a surface that's just a disk, right? Garden variety, right? Constant integrand. Life is good. We know that area. Easy computation. Everybody all right? Good deal. Okay. All right. Moving along. Y'all remember this business here about oriented density. I just want to remind you where we were coming from when we first wrote this down. We made an accumulation argument that ended up with a version of the fundamental theorem of line integrals that we had written like this. And the merits of writing it like this include that this thing right here, gradient dot t, is our density. You can see it right in the equation here. Change is change per unit length times length. Right? Very natural, very simple. There's our change density. But then we observed that, here's the thing though. TDS happens to be our dx vector, and so it's really kind of more elegant to write the theorem like that instead. And having done that, the natural question to come up with that we come up with is that, okay, well, yeah, but now what is this integrand, the gradient by itself? And the case that I made was that, okay, look, let's look at how that is equal to this. And, we like to say stuff is stuff per unit size times size. This dx vector isn't really a size, but it's an oriented size. Its magnitude is the size, but it also has a direction. The direction's just also telling you orientation. So I like to think of this as being oriented size, and as such then the gradient, our actual integrand, is an oriented density of our accumulating quantity being changed, and so that's the term oriented change density. And I know it's a mouthful, and I know it's probably not your favorite way to think of the gradient vector, right? But this is a valid way of thinking about it. And for segue purposes, this is extremely valuable. So in particular, when we say oriented change density, notice you can see the change density itself right there. The magnitude of the gradient is our sort of scalar change density. And then we also just have this orientation, u. That's the oriented part. That's just telling you what direction the change is happening in. That's telling you the uphill direction, right? That's what gradients do. They point uphill, right? So oriented change density because the magnitude is the change density and the direction is pointing uphill. That's the direction that the change is happening. Is that cool? All right. Okay, so shockingly analogous interpretation for curl. So now again, I'm a big believer in analogies, right? I urge you to try to digest this point of view. Try to get real comfortable and happy with the idea of thinking of the gradient, direction and magnitude that it is, that the gradient is an oriented density with its magnitude and its direction playing these telling us natural information about what we're dealing with. And then everything that happens with Stokes' curl theorem right here, it's all the same thing. All structurally the same. Different details. Yeah, sure, of course. Right? But structurally the same. So, again, what we just did, we just went through an accumulation argument. We wrote this down, and we appreciated the point of view that all this together is our circulation density, and then we can make clear claims like stuff is stuff per unit size times size, right? All that stuff we already talked about. Then we observed that, oh my God, look at that. That's the n ds scalar. Well, that's exactly our ds vector. So we wrote this down. And now let's try to take the analogous point of view on, let's see here, this equation. This is stuff, but ds vector is no longer just a size. But it is an oriented size. Its magnitude is literally the size. It just also has an orientation as well, right? So if this is an oriented size, then again, it's a pretty reasonable take that this curl itself is an oriented density. And again, all the same sort of analogous arguments here. The magnitude tells us, in some sense, I mean, look, it's literally this. It's telling you how much is the fluid kind of rotating around, thus creating circulations that we're computing. So it's telling you how powerful is this tornado or whatever it is, this whirlpool, this rotation of fluid, how much of a rotation is there? And by its direction, it's telling you in what direction is that rotation happening. And more to the point, it's telling you the axis around which that rotation is happening. So strongly analogous to these interpretations over here. The magnitude of the gradient tells you how much change is happening. The direction tells you in what direction is that change happening. Same story down here. So here's the way to visualize it. This is a really nice point of view. I think this is important to have in your heads when you're trying to make use out of curl. I mean, again, this is in your future. You're engineers. You're going to be doing E&M and stuff like that. When you see curl, I encourage the following point of view, and that is the direction that the curl points is just telling you what axis the fluid is, in some sense, in whatever sense, kind of rotating around. Whatever rotation there is of our fluid, that's the axis that rotation, whatever it is rotating around. And then the magnitude of the curl is in some sense a measure of how powerful of a tornado is this? Is there a lot of fluid rotation, right? Or is it a sort of a gentle flow around an axis? This tracks very nicely with intuition in the following two examples. These are two examples. You'll notice it's the exact same vector field in both examples. This is just geometry. There's no math in this. There's no algebra in this. A lot of math, no algebra. The kind of the rotation of the fluid, notice in this first example, pairs up with the direction that the boundary itself is kind of rotating around. So you're going to get a lot of boundary circulation because the rotation of the fluid and, if you will, the rotation, if you will, of the boundary line up. And that is not coincidentally, but geometrically unavoidably connected to how the curl that the fluid is rotating around and the normal vector that the boundary is kind of rotating around also point in the same direction. Right? So the idea that curl dot n, the idea that this dot product, curl dot n, should tell you how much the fluid is flowing along the curve lines up with the geometry very nicely. Right? And then just for contrast purposes, notice that quite the opposite if they don't line up. Right? So if the fluid is kind of rotating that way, but the boundary is kind of rotating totally different, right? There's no circulation happening there. The fluids go in a totally different direction from the boundary, and then likewise, the curl is pointing a totally different direction from the normal vector. Right? So the way these two vectors dot is unavoidably tied up with how these two sort of circles line up. Okay, good place to draw the line. Y'all have a good rest of your Monday. See you later. Picking up here next time. Don't forget about attendance if I didn't already get you.
Yes.